do the transformations in the GCSEs. You need to know the rules and you can do them with ease. There are only 4 of them, it's really a breeze to move an object given on a pair of axes. You'll find out how to do them if you listen to me. So the things you need to know are these: reflections, flip over in the mirror, rotations, spin around the center, translations, move up or down and sideways, enlargements get bigger or smaller.
Hey everyone, welcome back to our big ideas. This is 4.4 in geometry. You guys are enjoying those transformation songs as much as I am. Alright, so we're looking at congruence and transformations in this lesson. We're going to identify some congruent figures, describe congruence transformations, and that's probably going to be the most challenging part, I would think, in this lesson. Otherwise, everything else is, I think, fairly easy. Let's just take a look at our cartoon here for the day. So out there on the track is a runner. He's pulled off to the side of the track. It says down there at the bottom, 24-hour trackside assistance. This is like 24-hour roadside assistance, but applied to the track here. And the guy's on his cell phone. I'm on the back stretch, about halfway down. I think it's a pulled hamstring. So he's waiting for, I guess, a tow truck to come or something, get him off there. All right, so let's look at our lesson now on page 109 for the vocabulary word there that says congruent figures. Here's what we want to do. It says congruent figures, and 2 geometric figures are congruent figures if and only if. Now remember, that's biconditional statement right there when we see if and only if. There is a rigid motion or a composition of rigid motions that maps one figure on to the other. And it says congruent figures have the same size and shape. So we've been talking about so far our translations, our reflections, our rotations, and those are all rigid motions, as we said, in each one it's a rigid motion. And so congruent figures are rigid motion or compositions of rigid motions. So if you have a transformation, that's a translation, reflection, or rotation, it's going to give you 2 figures, your new figure and your original, and those will be congruent figures. So you can see here's an example of congruent figures. They're all the same size, same shape, even though they're kind of in different spots in different ways here, but they are the same size, same shape. Over here, not congruent. These are not the same size, not the same shape, so these are not congruent figures. So what you want to write down for this one in your vocabulary, just write down what this says. Congruent figures is a rigid motion or composition of rigid motions that maps one figure onto the other. And you could say they have the same size and shape for congruent figures. Okay, so here's an example. You do not need to write this down. Let's just go ahead and watch this. It says identify any congruent figures in the coordinate plane. You can kind of see what they are here. You can see obviously these 2 squares here are congruent figures. They're the same size, the same shape. You have these 2 triangles right here. So EFG and KLM, these are 2 congruent ones. And then these triangles here also same size, same shape. You can kind of just look at that and see that. I mean, you can definitely tell that from even just how they are here, 2 this way, and that's what's going on here. But what transformation, because it says explain here, and that's really what we want to, I think the harder part of it is explain. You can identify them, but then explain it. So what's happening? And so for this first one on the square, from one square to the other one, you can see it says that it's a translation of this AB. So if you start with the ones that are the lower on the alphabet, A, B, C, D here, it's 2 left and then 6 down to get to the NPQR square down here. So 2 left, 6 down, that's what that is. It's just a translation. For the triangle, the KLM, that's the one here, is a reflection of the EFG in the x-axis. And you can see that because they're exactly the same distance away from the x-axis here. One this way, one that way, right from just this side of the square of these triangles. And then you can see how it's flipped. It is flipped over the x-axis. So it's definitely a reflection over the x-axis. And then for our last ones here, these two triangles, let's say rotation, it's a 180-degree rotation. You could see, well, you know, for this one, it's in the second quadrant, that one's in the fourth quadrant. That's definitely 180 degrees. You know, if it was 90 degrees, it would maybe be down here, but going 2 quadrants away is going to give you more of an 180-degree rotation, and that's what's happening here, as you can see what happened. So that's what we want to do on number 1 in our extra practice. So on page 110, it says identify the congruent figures in the coordinate plane. And so let's go ahead and identify these first, but then we also want to, you know, jot down for each one perhaps which, you know, transformation maps one to the other. And I think that's, again, the harder part is the explaining part. So just get a highlighter, or actually you probably need like 3 highlighters or 3 colored pencils or something like that, something to have a different color in them. Maybe different pens is fine too, a blue pen, a red pen, whatever, green pen. But let's go ahead and, I'm going to use a highlighter here. So I'll highlight maybe one in red. So obviously we can see here's a congruent figure. So this one right here, I'll put it in red here. And with this one down here, these are congruent. So I'll highlight those in red. You can just fill it in, kind of like shading in that box. We can I'll do this one in blue here, the diamond shapes right here. So that's the congruent one to this also other diamond shape down here. Those are congruent figures. We can see that by just the fact that they're all the same size and shape. And then the last one, these are also the same size and shape. You can see even how the line here, this side right here is 3 units long. This one's 3 units long here. This one's going to go same 2 down and 1 over. This one's going to go 2 over and 1 down. It's the same 2 and 2, 2 and 2. So it's exactly the same size and shape. Now let's do that. I'll do that one green, I guess. So green right here. So any colors will do. You can pick your colors that you want to just make them into. So it just highlights the ones that are congruent. So it helps us out. And now let's figure out what's happening. Okay, so try to figure that out. Go ahead and pause the video and see if you can figure out what's happening with these rectangles, what's happening with these diamonds, and what's happening with these triangles. See if you can identify what the transformation is. Just one transformation to get one figure to the other figure. So see if you can think about that, and then I'll show you the answer. Okay, so hopefully you've thought about that. You try to maybe write down what you thought for each one of these different colors. So the red one, the green one, the blue one. So here's what we could have. So we already said all of this, what's all congruent. It's what we did with the highlighter here, basically. But here's what they said. So for this right here, for our rectangles, it says that it's a translation 5 units down. So the MNOP. So actually, no, that's these guys right here, not the rectangles. These guys right here, which are quadrilaterals, like a diamond shape. MNOP, that's the blue ones here. Translation 5 units left and then 2 down. So 5 left and then this way, and then 2 down from going from this one to this one. And then the other one, let's see, so now we got the ABC, no, not STU, that's this one here now. So now we're on our red ones. So the red ones is a reflection in the line of y equals x. So if we think about the y equals x line, I'll do it a little bit of a yellow here. So y equals positive x, that's the line that's kind of going right through here, through the origin, and it's just a slope of 1. So it's that line right there. If you can think about reflecting it over, it's reflecting over this. So every point basically is just going to be switched. So you can kind of see how the points are. Even just start there, G point here. So that's 1, 2, 3, and then 1, 2, 3, 4. So 3, 4 becomes basically or I should say negative 3, 4, becomes 4, negative 3. So 4, negative 3 puts us at U right there. That's what's happening on that one. And then the last one here, this triangle, it's a 90-degree rotation, really from one triangle to the other. Now it's saying, okay, from J, KL, that's this one over to here. That would actually go clockwise, but you could go counterclockwise to get to this one. So either way, it's a 90-degree rotation. You're just turning it 90 degrees about the origin here. The origin would be the center point. You can kind of see that as well. Maybe I'll just put a little, let me do I'll do a purple line here. So if we think about our first letters, J and P are our first letters. So if I go from J down to P, right there, and then, P to 0, 0, and then J to 0, 0, just kind of make that's a 90-degree angle right there. It's a 90-degree rotation then, from that point to that point, or back and forth. All right, let's move on to our next ones. Okay, so back on page 109, another vocabulary word here is congruence transformation. So just another name for rigid motion or a combination of rigid motions is a congruence transformation. So if we're only going to use the three rigid motion ones, the translation, the reflection, and the rotation, if that's all we're going to use, there's just those three there, then we're going to be doing a congruence transformation. There is one more transformation that's called a dilation, which enlarges or shrinks down a figure and changes its size and shape. So these ones, though, the translation, the reflection, and the rotation are rigid motion. So you can just say it's another name. This is another name for rigid motion or a combination of rigid motions. Okay, so here 2 and 3, these are probably the two hardest ones I think in this lesson, because we have to describe the congruence transformation, what is happening to get from one figure to the other figure. So it says describe the congruence transformation that maps PQR, the triangle PQR, so this is going to be our original, to STU. This is going to be our new one. So this would be the pre-image, this would be the image. So we got to figure out what congruence transformation, because they are the same size and same shape. They're congruent figures, but what's the congruence transformation? And it could be more than just one. It could be also a composition of rigid motion. So it could be a translation and a reflection, or a translation and a rotation. It could be more than one. And we're going to see that it is more than one on these ones. And there's also more than one way to state the answer. So you can do more than one way to get from one figure to the other figure. So why don't I have you try this? So go ahead and pause the video, see if you can kind of figure out how to get from this figure here with PQR to this one over here, STU. What do you need to do to get from this figure over to this one? That's going to map it here to that. And just think about translation, reflection, or rotation, and you're going to have two of them. So it's going to be two of those three you're going to have to do. So go ahead and pause it and then see if you can figure that out, and then I'll show you the answer in a minute. All right, so hopefully you paused it, you tried this number 2, and the answer I show you is just going to be a sample answer, because there is more than one way to get the answer. So you may have did it correctly, but it may not be exactly what this says. So this one says translation, 5 units up, followed by a 180-degree rotation about the origin. So if we think about this here, if I translate this one 5 units up, so P right here goes 1, 2, 3, 4, 5. Now I'm up here. Q goes 1, 2, 3, 4, 5. I'm here. And R is 1, 2, 3, 4, 5. I'm here. So if that's now our triangle right in here, and then we do a 180-degree rotation. So this is like maybe our P prime, our Q prime here, and this could be R prime right there. And then if I do a 180-degree rotation about the origin, when we do that, we're going to basically just change all of the points to their opposites. So if we think about where this P prime is, that's going to be over here at 4 and 5. So 4, 5, if I change both of those to their opposites, that's the rule that we learned for rotation of 180 degrees. That's now just going to be -4, -5. So if I go -4, -5, now I'm down to S right there. And that's the point that coincides, because the first one is P and the first one's S there. Those are corresponding points on the figures. So if I marked it off to U, that's not going to work, because P and U don't correspond in our congruent statement here. So that's what's happening here. You could do that same thing to all the other points to map them there. You could also see if you drew a line from the origin up to P, okay? And then you can see exactly what the slope would be for that. It would be exactly the opposite slope this way. It would actually have to have the same slope, basically just the opposite direction down here. So I would go up 1, 2, 3, 4, 5, and then go over 1, 2, 3, 4. And so I could just do the same thing, but just the opposite direction. So I'm going to go over, but instead of going right 4, I'm going to now go left 4, 1, 2, 3, 4, and then instead of going up 5, I'm going to go down 5, 1, 2, 3, 4, 5, and that does the same exact thing. All right, number 3, same thing here. We got two quadrilaterals. They are congruent figures, but we want to describe the congruence transformation from A, B, C, D to E, F, G, H. So we're starting here. Here's our original. We want to get to this one. So think about what you would do, and again, it's going to be 2 of them. It's a translation, rotation, reflection. 2 of those you're going to have to use to get from one figure to the other, to get from this A, B, C, D down to E, F, G, H. So go ahead and pause the video and see if you can figure out the 2 that you would use and what you would do. All right, so hopefully you thought about number 3, and you now just check in to see if yours is along the same lines as me and what the book says here. Again, it's a sample answer, so you could have had a different way of doing it. So this sample answer says a reflection in line x equals 1, followed by a translation 2 units right and 5 units down. So the reflection in this line x equals 1. So if you remember, x equals 1 would be right here. This line going right up here. I'll do it in yellow. So here's our 1, number 1, because it's 1, 2, 3, 4. So this is number 1 here. Oops, let me do yellow. So this is our reflection line we would do. So I can just put it right there. And I can reflect this point. So 1 this way, I'm going to go 1 that way. I'll do red. Here's my new C prime there. B is 5. So 5 this way on that same lines. Put me over here. So here's B prime. And this is C prime. Let's see, this is 2. Wait, did I do that right? Let's see, 1, 2, 3, 4. No, I did this. B is way too far away. I think I got mixed up with the y-axis on that one. So yeah, from our reflection line, not from the y-axis, our line of reflections, here's our mirror. So 1, 2, 3, 4. So from here, 1, 2, 3, 4. There it is. Right there. That's really B prime. So 1 and 1, that works out. And this one's 2, so 2 this way. There's our D prime. And see, this one is 1, 2, 3, 4 as well, same as B. So it's just on the axis though. So there's our A prime. And then we can see where the figure is now from just after doing that. It should still be a rigid motion, still should look the same. Yeah, it looks pretty much the same there, just flipped over that line of reflection. And now they're saying, okay, well now we got it kind of the same direction as this one is, and now we could just do a translation 2 units down. So if we just go, 2 units to the right, sorry, 5 down. So 2 to the right, so we go 1, 2 for A, and then 1, 2, 3, 4, 5 down, maps it to E. And that's where it is. A and E are the start of this one, so they are corresponding points of those figures. And that's really just how you can see that. So you just got to make sure to map on corresponding points there. And so that's one sample way. You could have done it also with the translation first. If you translated first and then reflected, you could do that. Could have been the same thing, and that would have been totally fine. Again, sample answer. Same thing up here. We could have probably done the rotation first and then did the translation. That would have worked as well. There might have even been a reflection that we may have been able to do that could have worked in there, but they say, okay, this is probably the easiest way to probably do it. All right, so on page 111, here's 4 and 5. It says to determine whether the polygons with the given vertices are congruent. So here's where we have to actually plot these points and connect the dots, make our figures, and then see if they're the same size and same shape. Are these congruent figures? And it says use transformations to explain your reasoning. So we can also write down what the transformation would be to explain our reasoning for that. So first of all, go ahead and just plot these two. I'll give you a moment here. Go ahead and pause the video if you can, and just go ahead and, on your paper, plot ABC, it's a triangle, and then plot DEF, and then see, do you think if it's congruent? Are these congruent figures? Alright, so hopefully you've plotted these and got the two triangles down. And so ABC should be right here, right above in the first quadrant. So there's where ABC should be. That's what yours should look like. And then DEF should be in the fourth quadrant down here, and it should look like this. And you should be able to recognize, yes, those are congruent figures. It looks like they are exactly the same size and shape. And what could we do to explain our reasoning with a transformation? Well, it looks like it got flipped over this x-axis right here. That's all that happened. It just flipped over. Remember the corresponding points here, A is going to correspond with D, B with E, C with F. So A is now D down here. If I flip it over, it's going to map onto this one. If I keep flipping these guys over, they're going to map onto their corresponding points. So that's what we can say there. We'd say yes, they are congruent, and that it's a reflection in the x-axis. That's what we can say. Number 5, do the same thing. So go ahead and pause the video. This one's going to be a quadrilateral. You have 4 sides here. So go ahead and plot all the points, connect the dots, and make your figures. See if you think they're congruent. Go ahead and pause the video and do that. Alright, so hopefully you got these down on your coordinate plane. So our figure for G, H, I, and J should be up here in the first quadrant. It should look like that. And then for K, L, M, and N, if you start plotting those points, you can see K is right there at 2, -1. L is -3, -3 over in the third quadrant. M is 2, -2 right there below the K. And then N says 2, -1, which is the same exact point as K. And so, you really only have 3 points in that one because K and N are exactly the same point. So there's no way that these can even be congruent. They're not the same size or shape. So no, this is not congruent here. So we say no, and really, they're given a lot of explanation here. Basically, the main thing is it's not a rigid motion. They don't correspond here. So you can even just say that K and N are even the same point. So you end up with just a triangle and a quadrilateral, and those can't be the same. So something left to this effect here, no, and something like that. They're not a rigid motion, you can just say. Alright, so we'll pause here for our joke of the day, which is this. What did one hat say to the other? You stay here, I'll go on ahead. Ahead. Of course, that's where hats go. Okay, so back to page 109, you'll see this theorem, which is reflections in parallel lines theorem. So basically, if you have 2 parallel lines, like K and M are parallel, they're showing little parallel marks. And if we do a reflection, so you have your segment here, AB, if you reflect AB over one of those parallel lines to get an A prime, B prime, and then do a second reflection over the other line that's parallel to get an A double prime, B double prime, it's the same thing as if you were to just go ahead and translate AB all the way over here to A prime, A double prime, B double prime. So as you can see, I could just move A and move B, and now it's a translation. So 2 reflections over parallel lines like this is the same thing as 1 transformation, or not transformation, translation, 1 shift, 1 move. And so that's kind of what it's saying here. Also, you notice this as well. It's got the distance between the 2 parallel lines saying that that's D. So whatever that is, if this is, let's just say if that was 2, then the distance from A to A double prime or even B to B double prime would be 2 times that amount. So if this was 2, then the distance here would be 4. Distance up here would also be 4 from the blue one to the green one. Alright, so 6 through 9 are using that theorem It tells us that K is parallel to M over here, so it tells us these are parallel lines, and that UV is reflected in line K, getting us U prime V prime, and that U prime V prime segment here is reflected in line M, resulting in U double prime V double prime. So it says here on number 6, a translation maps the UV segment onto which segment? So this segment here, a translation maps this segment to which one? Well, obviously it's not this one here. It would be right here, over to here, U double prime V double prime. That's what it would map it to. Translation is going to map it across both parallel lines, because you have one reflection and then another reflection. It's the same thing as if you did a translation from the first figure to the last figure. And number 7 says, which lines are perpendicular to U V double prime? So from this right here, if I were to draw a line from here to here, which lines would be perpendicular? Well, that would be your parallel ones right here. These are going to be perpendicular to a line drawn from U to U double prime. So that's just line K and line M. Those are perpendicular. It should make sense that that's true. And then, why is V double prime the image of V? So why is V double prime over here the image of V? Well, because remember you have a, this would be the image of our V prime with this reflection. Or this would be the image of V from a reflection as well. But this can be the image of the original V with a translation, so that because of a translation, that can be the image then of our original V. That's what it's going to say here. Because line K and line M are parallel, that's why. Because those lines are parallel, that's why it can be just one single translation. So we don't have to go to this one, we can just go straight from here over to here, and that's what happens to say that that is the image of this one. This can be the original for this one using a translation. And it says if the distance between K and M, right here, if the distance between these two parallel lines is 5 inches, then what's the distance between, or the length of V to V double prime? So our distance from here to here, which is what we just talked about, it is twice the amount. So whatever the distance here between this, the distance between U to U double prime or V to V double prime is always 2 times that amount. So 2 times 5 would give us 10. So it's 10 inches. Okay, one more theorem on page 109. And this is one where it's not parallel lines. We have 2 lines again. They're just intersecting lines. So they're not parallel. They're going to intersect. So you have your line M, your line K. Those are intersecting now. You have more segments. Here's your AB, there's your A prime, B prime, here's your A double prime, B double prime. And so what it's saying basically, if you start here with your blue one, and we do a reflection over K, and then do another reflection over M, this time it's the same thing as doing a 90-degree rotation from the original one here all the way over to the double prime one over here. So it's a rotation all the way over here. So it can be a rotation then. Actually, it doesn't have to be 90 degrees. Sorry, not 90 degrees. I got confused. It's just a rotation. It can just be a rotation. So it's the same thing as doing a rotation. And actually, the amount of degrees of the rotation, yeah, this is where I was confused. It's this right here gives you an angle. So that tells you X degrees. So this will be maybe 30 degrees right here. So if this was a 30-degree angle in here, then your angle of rotation from AB to A double prime, B double prime would be 2 times that amount. 2 times 30 would be 60. So it would be a 60-degree rotation then from that. All right, let's go ahead and apply that as well. So 2 reflections over intersecting lines also can become the same as 1 single rotation across those 2 intersecting lines. Let's go ahead and apply that to our next one. So this is our last problem here, number 10. What is the angle of rotation that maps A to A double prime? So here's our intersecting lines with K and M. Shows us that the 60 degrees here, well, vertical angles tells us that it's 60 degrees also on this side. So the in-between here is 60 degrees. So it's always twice. So from going from A all the way, the rotation, the angle of rotation, all the way over to A double prime, will be 2 times 60. So that's going to be 120-degree rotation then for that. All right, so that concludes our lesson here for 4.4. We'll be ready to then do our 4.4 assignment in class, and I'll see you guys there.